If we restrict ourselves to a special kind of collisions, those in one dimension, so like two trains on a track, and elastic, and remember we've said these don't really happen, but we're going to play like we do, we get very significant simplifications in the problem. So again, we'll say mass 1 is a projectile, mass 2 is a target, and we have two equations. And we get 1 out of momentum since it's one dimension. It says initial momentum of the projectile equals the final momentum of both pieces. If we're going to say it's an elastic collision, we get to make this rare equality, kinetic energy of the projectile at the beginning, the sum of the kinetic energy of the projectile. You do a little algebra, and I show this in the book. You get V1 final in terms of V1 initial and V2 final. There are three cases though, especially for V1F, and notice M2 is so small it's you get M1, M1, therefore the freight train doesn't really change the same. The tennis ball, on the other hand, is when we get rid of M2 because it's so small, we get the tennis ball flies off at twice the freight train. Of course, it doesn't just get the freight train speed, or the case where M1 is much less than 2, that would be like you've got a parked train and you hit it with a tennis ball. We put in our numbers here, and notice because M1 is the thing that's about 0, we get V1F is negative V1I. So the tennis ball comes back at you just as hard as you threw it at the train. And of course the train's velocity is going to be 0, it's not 1. One more special case, what if the two masses are the same? Then we get V1F is 0 and V2F is V1. So the projectile stops dead and the target takes off at the same speed. You see this sometimes in pool. You see this with the Newton's Cradle toys, the collection of little spheres on strings that you pull a couple back and they start clacking back and forth. Remember, we can only use these if we have elastic 1D collisions. But the thing that it does point out is the most efficient way to accelerate a target is if you hit it with a projectile with the same mass. The tiny projectile, the tennis ball, won't accelerate the target at all. And yes, the freight train will accelerate the tennis ball, but it takes a huge amount of energy to get the train moving at half the speed you want the tennis ball to end up with, so that's not very efficient either. This idea is called impedance matching, and it pops up all through physics. You'll see it next semester in electric power transfer. It's the reason we use water in nuclear reactors for a moderator, and it's also the reason if you've ever had to have an ultrasound, the technician will put this kind of gel on the ultrasound wand before they touch your arm or whatever with it, and it's to match the impedance between the wand and your body without having to go through the air, where it would not match well at all. Now that we know the real form of Newton's second law, we can go back to that and look at a special case where dm dt is not 0. Let's say, for example, you're on a frozen lake, you're on a sled, you have a machine gun, and it fires 10 bullets per second, each 20 grams mass, each one traveling at 500 meters per second. Let's say the total mass of everything when you start is 150 kilograms. If you start firing from the back of the sled, it'll start moving forward. What's the recoil force? Well, since F is also V dm dt, it's not just this piece, but we have this piece, V dm dt, we know we're losing mass at the rate of 0.2 kilograms a second, 0.02 kilograms per bullet times 10 per second. The bullets are moving at 500 meters per second, so if I multiply V times dm dt, I get 100 newtons. We can use that to find the acceleration of the sled. 100 newtons applied to a 150 kilogram sled will give us 0.667 meters per second squared. In reality, it's a harder problem because the acceleration will actually increase a little bit as time goes on, since this 150 kilograms is dropping by 0.2 kilograms per second. This is just the rocket problem. That's what this is known as. This is the way rockets work. Anything that propels itself forward by ejecting mass with some velocity backward is a rocket. If you blow up a balloon and let it go, it's acting like a rocket. We can take this force law that we found up here, and we can use it to get the first rocket equation. This is derived in your book, where R is the mass loss rate, the dm dt. V-rel is the relative velocity between whatever you're throwing out the back of the rocket and the rocket itself. Those two equal ma, where m is the rocket's mass and a is its acceleration. That's what we just used in this problem up here. The second, when we actually integrate it, we take account of the fact that the mass is decreasing as time goes on. So we can say the incremental change in the rocket's velocity dv is negative relative velocity times dm over m. We know that dm will be negative. If we integrate and solve for v, we get that the final minus the initial velocity is exhaust velocity times the natural log of initial over final masses. This, of course, doesn't include the action of the force of gravity, so this would be like if you built the rocket out in space and fired it. Notice that it's very hard to increase the rocket's final speed this way. If you want it to go twice as fast, you can't just double the initial mass for a couple of reasons. One, because of that log function, this is about the most slowly increasing common function there is. Doubling the mass would only increase the final velocity by 69%. It wouldn't double it. Also, if you double mi, mf is not going to remain constant. Mf is what's left over when all the fuel is gone, so it's the tank. You can't have twice as much fuel with the same size tank. This whole reason is why we have multi-stage rockets. You could start getting rid of the fuel tank that you don't need anymore after the first few seconds. So this rocket problem, the key to space travel is to not have this logarithmic function screw everything up, to use multi-stage rockets.